Professor? Professor?
Yep, can you hear me okay, Ivan?
Yep.
Great. All right, let's get started then. Okay. We're all set, live stream on. Hello, good morning, everybody. I hope you're having a nice week. Hopefully you were able to enjoy the day off yesterday and get a little rest and relaxation. Just a quick reminder that our Chapter 4 quiz is today. So at some point today, you need to find a 1 hour period to take your Chapter 4 quiz. If you are unable to attend the review, the link to the review recording is posted in Moodle. It's listed under the Getting Started tab with all the other review videos. So if you want to check that out before you take the quiz, that's where it's located. So today we're going to be starting Chapter 5, and it's the last chapter that we cover for our class, so it's very exciting. And as we sort of go through the Chapter 5 stuff, you'll see tiebacks to things we've been learning all term. So we're going to get going. I'm still a little bit sick, but hopefully my voice will hold out for the class, but Ivan can let me know if you guys can't hear me. So just to sort of give you an overview of Chapter 5, when we were working through chapters 2, 3, and 4, we were asking, how do we find the derivative? What is the derivative? And what can we do with the derivative, right? So it was all about rates of change. And Chapter 5 approaches it by saying, okay, well, what if we know the derivative, but we don't know the original function? Like, what kind of information do we have if we only have information about the derivative? And we've talked about this in small little bits because we know things like if the derivative is increasing, the original function is positive, right? Things like that. Or if the derivative is positive, the original function is increasing. Sorry about that. So we're going to look at what kind of information we can get from the derivative about the original function. That's sort of the take of Chapter 5. What if we start with the derivative? So that's where we're headed. I'm going to go ahead and switch over to the dot cam here. Okay. And so the way we start with this is we talk about something called accumulated change. Okay. And we start with this idea of distance to help us understand and visualize how accumulated change is going to work. So the first thing we need to know is that distance is going to be velocity times time. And this comes from physics. If you've not taken physics before, that's okay. And so velocity is something like, 5 feet per second or something of that sort. So how quickly your rate of change is changing times the amount of time that you are going that rate, that will give you the distance of whatever the moving object is, right? So for example, if you're going to travel 40 miles an hour for 3 hours, how far did you travel, right? So this is exactly the type of problem that would come from this distance formula. How far are you going to travel? That's the distance. The distance is the rate times time. The rate is 40 miles per hour times the time is 3 hours. We go 40 miles an hour for 3 hours. We see that the hours units cancel. And we get 120 miles. So that's the distance that we traveled during that time period, okay? So that's sort of how we typically use this formula. But we can also represent this graphically, and this is different than how we usually interpret and look at graphs. So let's see what that might look like. So if we were going to graph this, we're going to put our rate on the vertical axis, and we're going to put our time on the horizontal axis, okay? So our rate here was 40 miles per hour. How do we graph 40 as a rate, right? So 40 is a constant. So we have some number, and it's 40 the whole time, but for how long? Well, for 3 hours, right? So time will be in hours. We go 40 miles an hour for 3 hours, right? So a constant, a number that's by itself is just a horizontal line. So if we look at the area between the line and the x-axis, that area is 40 times 3, right? Because area of a rectangle is length times width. And that is 120. Well, that's the same 120 that we got by calculating this up here, okay? So what does that help us understand? That helps us understand that the change of the original function, distance, can be represented by the area underneath the curve. We call it a curve, even though it's a line, right? This will eventually translate into curves. But this is called accumulated change, right? So this picture represents this algebra story, okay? So let's see if we can sort of expand this and do a similar problem that has 2 legs to it here, right? So let's say you were going to travel 20 miles an hour for 3 hours and then 50 miles an hour for 4 hours. How far did you travel? So we want to compute this algebraically and graphically. So you want to set up the distance equation just using algebra and then draw a picture using the rate and the time and see if you can graph what this might look like. Okay, so I'm going to give you 2 minutes. This is not any more difficult than you think it is, right? It's not super difficult. It's what you think. You're going to be multiplying distance times time plus distance times time, and then thinking about how you can translate that in this similar way. So take 2 minutes, see if you can work that out, and then we'll go through it together. Okay, so take about 30 more seconds to finish up whatever part you're working on. Okay, so we can actually break this down into sort of 2 legs of the trip, right? Because we have 2 different rates for 2 different times. So for the first leg of the trip, we're going 20 miles an hour for 3 hours, right? So we have 20 miles per hour times 3 hours. Again, the hours units are going to cancel. And we get 60 miles for this first leg of the trip. For our second leg of the trip, we see that we're going 50 miles an hour for 4 hours. So we have 50 miles an hour for 4 hours. Again, the hours units are going to cancel. We multiply those together, and we get 200 miles for the second leg of the trip. So if we want to know how far we traveled in total, we would need to add those 2 together, and we get 260 miles. Okay, so that's like the first part. That's how we algebraically determine how far we traveled. How do we translate this into a graph, right? How do we draw a picture of what's happening here? So again, we're going to have rate versus time. Our rate is in miles per hour. Our time is in hours. So for the first leg of the trip, we're going 20 miles an hour. So let's throw a 20 on here. So say 20 is here. So the first leg of the trip is 3 hours long, right? So let's say that that is 3 hours, right? Something like that. So 1, 2, 3 hours long. So the area underneath this line here is 20 times 3, which gives us this 60 miles. That's the first leg of the trip, okay? Now the second leg of the trip, we're going 50 miles an hour. Now, so if 20 is here, 50 is probably somewhere up here. The 50 miles per hour starts after the 20 miles per hour ends, right? Like it's a second leg of the trip. So from here, we're going to start at 3, but we're going for 4 hours. So we're going to go from hour 3 to hour 7. Right? Because that still represents a 4-hour trip, but the second part starts afterwards. And we just know that because it's, the word then. So this happens first and this happens second. So for the second part of the trip, if we look at the area, right? The width is 4 hours. The height is 50 miles per hour. So that area is 200 miles. So we would add the areas together, 60 plus 200, and we would get that 260 that we got from this setup of the algebra, okay? So this is an example that's meant to help you visualize how we might graph the rates here. We don't always have to do this with distance, okay? So now we're talking about transferring this to something else. So in these two scenarios, distance, right, was based on the original function of position. We were using the derivative of position to talk about how much the position changed. But we can do this with other rates of change that are not distances. And so we're going to do an example next that looks at a different type of rate of change about a population, and we're going to try to apply the same process to a different scenario. So here, suppose the population is growing at a rate of 2,000 people per year for 3 years, and then 3,000 people per year for 4 years. What is the total change in population over those 7 years, right? So we're going to approach it the same way we did here. There's sort of 2 different periods of time. We want to figure out how much it changed in each of those periods of time and add them together. And then we want to try to graph it. So I want you to take 2 minutes, see if you can sketch this out and come up with the algebraic answer to figure out how much the population changed. And then we will go through it together. Okay, take about 30 more seconds. Okay, so again, we're looking to figure out how much the original population changed by thinking about the rate of change and how long we were at that rate of change. So we start with this rate of 2,000 people per year. Per year, and we're doing that for 3 years. So if we're changing at 2,000 people per year for 3 years, we multiply those together, the years cancel, and we get a change of 6,000 people for this first part of the growth. Secondarily, we grow by 3,000 people per year, and we do that for 4 years. Again, the years are going to cancel, and that means during that period, we grew by 12,000 people, okay? So that means the total change in population over these 7 years, we're going to add these two together, we get 18,000 people, okay? And so what's important about this number, before we talk about the picture, is that that does not mean that the population is 18,000 people. That means that whatever the population was grew by 18,000 people. How do I know it grew? Because it was positive, right? If it was a negative number from a negative rate, that would mean we were losing people. But I don't know what the total population is because I don't know what it was before we started. If I did have that information, let's say, we knew that the population started at 50,000 people, then I could add the growth to it to get the new population. But what this is telling me is how much the original function changed, how much the population grew over those 7 years, which is different than what the population is. So that's an important distinction, okay? So now let's go ahead and draw the graph. Okay, so we have our rate, which is people per year. We have our time, which is in years. We know we're looking over a 7-year period. And we know that our rates are in the thousands. So we have 1,000, 2,000, 3,000. We'll put 4,000 on there for good measure. So for the first part of the growth, it was 2,000 people per year. That's our rate. And we did that for 3 years. So we have this constant between year 0 and 3. And again, if we multiply and we get the area of this rectangle, that gives us 6,000 people. And then from years 3 to year 7, that 4-year span, we're at 3,000 people per year. So that's up here a little bit higher. And for that time period, we grow by 12,000 people. Okay, so we're able to take this algebraic sort of calculation and find the same information on the graph. Now, the question really becomes, why do we want to graph it this way? Like, what is the benefit of doing the graph versus just doing the calculation? Because to get the same information, right, the change in population. The reason why we want to learn how to do this graphically is because when we get rates of change that are not constant, we can no longer use the same type of algebra, but we can still use a graph. Okay, so that's going to be our goal. So our next step is to ask, okay, well, what if it's not constant, right? Instead of 2,000 people per year, what if it's a function, right? Number of people per year, or what if it's a curve or something like that? So the next example we're going to look at here looks like this, right? Where we have the rate at which a skateboard is moving over a 60-second interval can be written by the function f of t equals 3t, with f of t in feet per second and time t in seconds. What is the total distance traveled by the skateboard over the first 10 seconds? Okay, so what's different about this problem? What's different about this problem is the rate at which we are traveling is now a function. If this was just 3 feet per second, it would be the same as the other problems. We would just graph that constant line and we would just multiply. But now we have a rate that is a function. Fortunately for us, it's a linear function. It's 3t. So what we need to do is we need to think about how we can draw this, because we can't just multiply like we did before. If we multiplied the rate times time, we'd be multiplying 3t times 10, which would give us 30t, right? So there would still be a t in there and we wouldn't know how far we traveled. We also can't just plug 10 into the function, because if we plug a 10 into the function 3t, that tells us the rate at time equals 10. That doesn't tell us the distance that we traveled. So our approach is going to be to graph this function. So you're going to draw 3t, and you're going to think about the area between the line and the x-axis and see if you can figure out what that area is. Okay, so I'm going to give you 2 minutes. Again, I want you to graph the rate just like we did before. So we have rate times time, or rate by time. You're graphing 3t and thinking about how you can use area under the curve. Again, it's a line here, to figure out the total distance traveled. Okay, so take 2 minutes, see what you can come up with, see if you can figure it out, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so when we have a function that is linear, right, like this, 3t, and we want to try to approximate the distance traveled, what we need to do is we need to rely on the graph to figure out the area between the graph and the x-axis. So what we need to do is figure out where we want to label 10. We're interested in what's happening over the first 10 seconds. And if we were to shade in the area we're talking about, what we see is that we have a triangle, okay? And as a reminder, the area of a triangle is 1/2 base times height, okay? When we were looking at rectangles, it was just length times width, or base times height. Here it's 1/2 base times height. So the question is, do we have all the numbers we need for this calculation, right? So 1/2, our base goes from 0 to 10. So that's 10 seconds. And what about our height here? Okay, so our height is the corresponding y value right, or dependent value when time equals 10. So if you were to plug a 10 into this function, that would give you the corresponding rate, which is also the height at that time. So here, if we plug in the 10, we get 30 feet per second. So if we multiply all those numbers together, we see that the units of seconds cancel. 10 times 30 is 300. We want half of that. We get that this skateboard traveled 150 feet. So we're able to use the graph here to determine the distance traveled when we weren't able to do it algebraically. Now, if your function is a constant, like we saw in the first two examples, or if your function is linear, like we see in this example, we can rely exclusively on areas that we know from geometry, right? So rectangles and triangles. However, if your function is curved, right, then we don't have nice geometrical shapes to fit in, right? So if you have something that's, curvy and you want to find the area, here, that's sort of our next step. How do we find that area? We don't have a good geometrical shape. We have arcs and things like that, but this is not a geometry class. So we're going to try to figure out how to find that area without doing just a geometrical representation of one particular shape. Instead, what we're going to do is we're going to rely on rectangles, which are the easier of the two shapes, to help us understand area under curves. Okay, so we are now moving from doing things algebraically to representing them graphically to help us understand this area. Okay, so in order to do this, we sort of have to take a step back to understand how we are going to use these rectangles to approximate these types of things. And the easiest way to start this is by thinking about data in a table. So let's check out this scenario here. So suppose we measure the velocity, v of t, in feet per second of a bicyclist racing down a flat road every 2 seconds. Okay, so let's make this a little more high stakes. Let's pretend that you are in a bike race. The person who travels the fastest over 10 seconds wins like $1 million or something really extravagant, right? And so we have some way of calculating how fast they are traveling every 2 seconds, right? So maybe we have something on their bike that's recording it, but we are able to get their rate of change every 2 seconds, right? How can we estimate the total distance traveled over this 10-second interval? And how do we graph this? So one thing that we can't do, right, is we can't just multiply our rate times time for every possible second. Why is that? Because here, let's imagine that we multiplied 22 times 10. What that would mean is that I was going 22 feet per second for 10 seconds, which is different than 22 feet per second at time 10. Okay, so we run into sort of the same issue that we had up here, that we can't just multiply these things together. Instead, we need to think about what this looks like visually and how we might approach this. Okay, so let's imagine now that this is the data we have and we are like the official judges. What we're going to do is we're going to take each time interval into 2-second intervals, because that's how we measure it, every 2 seconds, right? So what we're going to do is we're going to consider what happens between time equals 0 to time equals 2, time equals 2 to time equals 4, time equals 4 to time equals 6, time equals 6 to time equals 8, and time equals 8 to time equals 10. Okay, so we're going to break this down into these little 2-second intervals that we have. And what we're going to do in order to use what we know to figure out what we don't know is we are going to fix the rate. What does that mean? We're going to pick a constant rate and say that for that 2-second time interval, we are going the same rate. So that brings us back to what we were doing in the very first example. We have a constant rate. So from time equals 0 to time equals 2, there's two rates here. There's 0 and there's 5. So there's a couple different ways we can approach this. But one of the key things about math is that we want to do things in a methodical way, right? So we want to do it the same every single time so that we are consistent and someone can follow our work. So what I'm going to do is for each time interval, I'm going to pick the rate on the left of the two. So I have 0 and I have 5. So I'm going to pick the rate 0. And so now I can do rate times time. My time is 2 seconds long, 0 to 2, times my rate of 0 gives me 0. Okay. Now from time equals 2 to time equals 4, that's another 2 seconds. So my time is 2 seconds. And now my rate, I'm going to pick the one on the left to be consistent. So that's 5. 2 times 5 gives me 10 feet for that 2 second interval. From time 4 to time 6, that's another 2 seconds. I pick the rate on the left, which is 7. So for that 2 second interval, I went 14 feet. From time 6 to time 8, that's another 2 seconds. I pick the rate on the left, which is 10. So I go 20 feet in that 2 seconds. And then from time 8 to time 10, that's 2 seconds. I pick the rate on the left. And that gives me 30 feet. So now I have a representation of how far I've traveled for each 2 second interval, and I can add them all up just like I add up the legs of the trip, right? So I do 30 plus 20 is 50, plus 14 is 64, plus 10 is 74. So here, my bike has gone 74 feet, okay? Now, if you were the person who was on the bike and you were going to win a whole lot of money if you traveled the farthest, you would be very unhappy with how I chose to do this, because I want you to notice that in the way I set this up, I didn't even use your best time. I didn't use the 22, right? Instead, I used 0, 5, 7, 10, and 15, but I didn't use the 22. And so what I did here is what's called a left hand estimation or a left hand approximation, okay? And what makes it a left hand estimation or approximation is that for each time interval, each little pocket of time, I always pick the rate on the left, right? There's no reason why I couldn't have done the same thing, but pick the rate on the right. Okay, so let's go ahead and do that. So what I'd like you to do is I'd like you to repeat this exercise, but for each 2 second time interval now, I want you to pick the rate on the right. So we'll do the first one together. From time equals 0 to time equals 2, that's 2 seconds long. From 0 to 2, I pick the rate on the right, which is 5. So for the first time interval, I'm going with 10 feet. So I want you to do that for each time interval, pick the rate on the right, and then add them all up and see what your right hand approximation is going to be, okay? So I'm going to give you about a minute and a half to do out those calculations, and you will find that we get something different, but we want to see in which direction and how different it is, okay? So take a minute and a half to complete the right hand approximation, and then we'll go through it together, and then we'll graph it. Okay, take about 30 more seconds. Okay, so here from time equals 2 to time equals 4, that's still 2 seconds, but now we're going to pick the rate on the right, which is 7. So 2 times 7 is 14. From time 4 to time 6, that's another 2 seconds. I pick the rate on the right, which is 10. 2 times 10 gives me 20. From time 6 to time 8, I pick the rate on the right. So I have 2 times 15, which gives me 30. And then lastly, from time 8 to time 10, that's 2 seconds. I pick the rate on the right, which is 22. And that gives me 44. So when I add up all these numbers, 44 plus 30 plus 20 plus 14 plus 10, I'm going to get 118 feet as a right-hand estimate. Okay, so we can see that the right-hand estimate is bigger than the left-hand estimate. Okay, so that is not always true. Sometimes the left-hand estimate's bigger, sometimes the right-hand estimate's bigger. It depends on the problem you're looking at. So what do I do with this information? Well, I know that my distance traveled has to be between the smaller number and the bigger number. So it gives me bounds. Okay, my actual distance has to be somewhere between 74 and 118. And so what we do is we call the bigger number the overestimate. And we call the smaller number the underestimate. And I would say about half the time, these are the numbers you're looking for. I'll say find the over and under estimate for the total distance traveled. The other thing we can do with these is to find the best estimate. And when you see the word best estimate, that means you are taking the information you have and making a best guess, right? And the best guess is going to be to find the midpoint by just averaging these two numbers together, right? So we're going to take 118 plus 74 divided by 2. And so our best guess here for the estimate will be 96 feet. Okay, so again, there's 3 distinct numbers that we are calculating here: the overestimate, the underestimate, and what's called the best estimate. So when we do this, there's a couple things that are important here. What I want you to note is that our time interval is always counting by the same thing. So we're counting by 2's here. So every single estimate is multiplied by 2, right? Because that's how we were counting in our time. And so we call that delta t is 2. So what you're counting by is called your delta t if your variable is t, or delta x if your variable is x. That's something that's going to come up as we're doing our work as one of the new notations. So why do we do it this way? How is this related to what we were doing before? Well, let's graph this. Okay, so there's 2 distinct graphs that are going to come out here. There's the left-hand approximation and the right-hand approximation. So we're going to do the left-hand approximation first to see what's happening. So from time equals 0 to time equals 2, we were assuming a rate of 0. So if we were graphing that, our rate would be constant and it would be 0. So it would just lay on this horizontal line. From time equals 2 to time equals 4, we were assuming a rate of 5. Okay, so we were making that rate constant from time 2 to time 4. From time 4 to time 6, we chose a rate of 7 because that was the one on the left. So again, we've made this rate constant from 4 to 6. So hopefully you're starting to see that what's happening in the background is that we've turned these all into rectangles. So from time 6 to time 8, right, we're going to be up here at 10. And then time 8 to time 10, we picked a rate of 15 as a left-hand approximation. And again, these areas are what we added up here, right? So 0, this has 0 area. 10, this is 2 times 5. This was the 10, right? And then 2 times 7, this was the 14 that we added up, right? From time 6 to time 8, that was the area of 20, which is 2 times 10. And then 2 times 15 was 30. So this was our left-hand approximation. By picking a constant rate for a particular time interval, that makes this into a rectangle, right? That constant rate is what gives us the ability to turn this into a rectangle. Now, when we did this with a right-hand approximation, we changed a little bit what we were doing. So for the first 2 seconds, we said that the rate was 5. So we're up here from time 0 to time 2. From time 2 to time 4, we said that that was going to be 7. So that's up here. From time 4 to time 6, we said that was 10. From time 6 to time 8, we said that was 15. And then from time 8 to time 10, we said that was 22, which is up here. Okay. So our red rectangles, right, gave us more area. And we can see that the red has a higher area than the black, right? So our right-hand estimate was bigger than our left-hand estimate. So what does this function actually look like? Well, if we were to draw in a sketch of what we thought this function would actually look like, we would be looking at a function that looks like this. How do I know it looks like this? Okay, when you do a left-hand approximation, the left hand of each rectangle touches your function. When you do a right-hand approximation, the right-hand point of each rectangle touches your function. So I'm able to connect these points to see roughly what the function is going to look like. And we can see that it's not a perfect line, and that's why we need to use these rectangles to approximate. Notice that the red area gives us more area than is actually under the curve, and we know that the red was an overestimate. The black rectangles here don't give us all the area, right? It's missing some of the area under the curve, which is why it's an underestimate of the area. So when we do this type of work on a table, what's happening in the background is that we are creating these rectangles to approximate this area under the curve, okay? So that's what the picture looks like. Now, as I mentioned before, there's delta t, which was 2, okay? And delta t, if we're counting by 2s, is the width of every single rectangle we draw. When I talked about being consistent in math, this is part of it. Every single width has to be the same, right? So our delta t here equals 2. Now, there's another notation that's about to come up on the next slide, but it's easier to show you here, which is n. N is the number of rectangles that we use to approximate. So it's the number we use if we're doing a left hand or a right hand approximation. So here, if we count 1, 2, 3, 4, 5, n is going to be 5. We used 5 rectangles to approximate. And we'll talk about what it means when we change that in a few minutes. So that's the picture. There's a lot of information here all at once. So let's sort of consolidate some of the stuff that we've been talking about and see how we can sort of summarize some of the things we've been doing, right? So we have estimates. We have left-hand estimates. When we do a left-hand estimate, we assume the rate on the left is constant. Okay, so we're picking the one on the left each time. Same thing over here with the right. We assume the rate on the right is constant. We do a right-hand estimate, the overestimate and the underestimate, but we're going to compare left and right estimate and pick the bigger one. Okay, I can't stress this enough that sometimes the left-hand estimate is the overestimate, but sometimes the right-hand estimate is the overestimate. So you have to do both and compare them. For the underestimate, we compare them, and then we're going to pick the smaller of the two. Okay. Now, what are the variables and the things we talk about when we do this kind of work? So delta t are the time intervals we're using to approximate. Okay, so last time it was 2, delta t equals 2 because we were counting by 2's. So what is the width of our rectangle and what are we counting by? N is the number of rectangles we are using to approximate. And then we have A and B. So we haven't talked about A and B yet. A and B are going to be the starting and ending points. As defined by the independent values. So for example, in the last example, A would have been 0 and B would have been 10 because we were doing a 10-second interval. Okay, now these three variables are all interrelated and they help us understand how the whole system is working. If you look at B minus A divided by N, so B minus A is the span of time you are looking at, endpoints, right? The difference between the endpoints. So you're looking over 10 seconds, 20 seconds, 30 seconds. If you divide that by N, the number of rectangles you want to approximate with, that will give you delta T. So if you don't have delta T and you need delta T, but you know A, B, and N, you can find it that way. Similarly, B minus A divided by delta T equals N. So if you know the two endpoints and you know what you're counting by, you can set this up and figure out how many rectangles are going to be used to approximate. Okay. So suppose now that we are going to do the same exact experiment that we were before, where we're looking at the 10-second interval. You're a bicyclist, you're racing. The only difference between the last problem and this problem is that instead of having data every 2 seconds, which is the same, right, at 10:22, at 8:15, 6:10, now we know the speed every 1 second, right? So we have that data. We've calculated how fast you're going every 1 second instead of every 2 seconds. So we want to do the same thing we did on the last table. We want to find the left-hand estimate. We want to find the right-hand estimate. And then we want to use that to find the best estimate of the total distance traveled over the 10 seconds. Okay. And so I want you to take the time to do the same process to find the left-hand estimate and the right-hand estimate, and then use that to find the best estimate. And then I want you to compare that to what we found when we were calculating every 2 seconds. And think about the question, is this a better estimate than the previous estimate, or is this a worse estimate than the previous estimate? Okay, so I'm going to give you about 2.5 minutes, 3 minutes. See if you can get that set up, and then we're going to go through it together. Okay, so try that out. I am going to go blow my nose, so I will be right back. And then we'll go through it together. Okay, take about 30 more seconds. Okay, so when we do our left-hand estimate, we are now looking at 1 second intervals. Our delta t here is 1, which means that every single rate is being multiplied by 1. So we have 1 times, now for the first 1 second, we're assuming the rate on the left, which is 0. From time 1 to time 2, we assume the rate on the left, which is 3. And then we keep going down the table like that. Plus 1 times 10, plus 1 times 12, plus 1 times 15, plus 1 times 18. So 18 is the last rate we use because from time 9 to time 10, that's another 1 second, and we pick the rate on the left, which was 18, but we don't use the rightmost rate. So we use all of the rates except for the rightmost rate. And so we do 1 times each of those numbers, we add them all up, and we're going to get 84 feet. Okay, when we do the right-hand approximation, we're going to do the same thing, but we're going to be picking the rate on the right each time. So for the first second, we're going to pick 3. And then we're going to pick 5. And then 6, 7, and then 8, and then 10, and then 12, and 13, oh, 15, and then 18, and then 22. So when we do a right-hand approximation, we use all the rates except for the leftmost rate. So we don't use the 0, but instead we use all the ones after that. So when we add all of those up, we get 106 feet, okay? So when we do the best estimate here, we're gonna average those together. So we get 106 plus 84 divided by 2, and we get 95 feet. Okay, last time we got 96 feet as our best estimate. This time we get 95 feet. But the question is this a better estimate than the previous one? So what does this information tell us? This information tells us that the actual distance traveled has to be between 84, which is our lower bound, and 106, which is our upper bound. When we did this with delta t equals 2, we're counting every 2 seconds, our bounds were 74 and 118. This is a smaller interval, so it's a better estimate. Okay, if you are able to shrink the interval of where your total distance needs to be, that's going to give you better information. So what does that mean? That means if delta t is smaller, which is the same as n is bigger, because those are related. As delta t gets smaller and gets bigger, we have a better estimate. Now, why is it better? Because we're fitting in more triangles, right? So instead of 5 triangles, we're fitting in 10 triangles that are skinnier, which means there's less room for error in how much we overestimate and underestimate. Okay, so we need to think about how this is going to help us sort of think about things and figure it out, which hopefully we'll have time to get to, but we'll see. So the figure below shows the velocity of an object over 31 minutes, right? I want you to estimate the total distance traveled using a left-hand sum with n equals 2, and to estimate the total distance traveled using a right-hand sum with n equals 2. So what we're trying to do here is we're trying to really connect what n equals 2 means and what it means to approximate using left and right hand sums with a picture. So we're trying to connect that visual with what we were doing algebraically. Okay, so I want you to think about how we might approach this. Okay, I'm going to give you 2 minutes to think about it. See if you can figure out how we might do a left and right hand approximation, what n is, and how that's going to help us here, and how we might put that all together. Okay, take about 30 more seconds. Okay, so what does n equals 2 tell us? Well, n equals 2 tells us that there are 2 rectangles that we are using to approximate, right? We also can use that to help us find things like delta t, because if we're going to put 2 rectangles in here, we need to know how big the base or the width of each rectangle is going to be. So let's just sort of write out what we know. So A is where our function starts, 0. B is where our function ends. We know that that's going to be 31. And we know that n equals 2, right? So how do we put this all together? Well, we can do b minus a over n to get our delta t. So b minus a is 31 minus 0 divided by 2. That means that my delta t is 15.5. Why do I need my delta t? That tells me the width of my rectangles. So here I'm going to approximate just about where 15.5 is, right? So I'd say just about here. It's about halfway, but a little bit more. But I'm going to label that just so I know what I'm talking about. So for part A, if we're using a left-hand sum, that means we need a rectangle that goes from 0 to 15.5, where the left-hand side of my rectangle comes up and touches the function, right? So that means that for the first 15.5 seconds, the height is going to be the height when I use the left-hand point of the rectangle. So that goes up as high as 20, right? So that means I have 20 times 15.5, which is going to give me an area of 310 for that first part. And now the second rectangle, because remember there's 2 rectangles, I have 15.5 to 31. I want the height to be based on the left-hand point of these 2. So I go up as high as I would until I hit the function at 15.5. That tells me how high to go. That's my height. And that gives me my second rectangle, right? And so now the height here, or the area here, is going to be 15.5 times, now I have to approximate this height, right? So looking here between 10 and 20, I'm going to call that 17. Looks about 17 to me. You might have said something slightly different than 17, but as long as you're close, that's fine. And that gives me 263.5 for this second rectangle, right? So this is a left-hand approximation because again, I'm using the left-hand points. I add these two areas together and I get 573.5. So that's how I tie in my left-hand approximation. When I'm doing my right-hand approximation for part B, now when I'm looking at my first rectangle and I have 0 and 15.5, I'm picking the one on the right. So I go up this high. And now my right-hand approximation, right, is going to be 15.5 times, I said that this height was just about 17. So that was 263.5 for this first right-hand approximation. And then when I choose between 15.5 and 31, I'm picking the one on the right, which is 31. I see that this is at 0, right? So that doesn't have any area because the second one is just right here. That's the height. So I have plus 0. So that means my right-hand approximation is 263.5. And I can see here that my left-hand approximation is an overestimate because I have more area than what's under the curve. And that my right-hand approximation is an underestimate because I have less area than what's under the curve. Okay, so even though we're doing things algebraically, they also translate to graphically, and we do need to be able to go back and forth. Okay, we are going to skip example 5, and we're going to jump to Riemann sums because you will need that more importantly. Okay, overall, putting this all together. So you can watch example 5 on the videos if you want to see that done out. So how do we sort of figure out the best way to do this? So we have something called Riemann sums, and Riemann sums are where we set up a sum that represents area under the curve in a general way. So what do we need to remember to set these up, right? So the delta t we can find by doing b minus a divided by n. So those are the two endpoints divided by the number of rectangles we want to use. In order to set this up, we need a way to index our rectangles in general. So we're going to use t sub 0, t sub 1, t sub 2, t sub 3, t sub 4, right? We're going to just, each point is going to be t sub something, where the last point is t sub n. So we call it t sub n because that's the number of rectangles we'd want to use. Obviously, in this picture, it would be t sub 4 because there's literally 4 rectangles, but we're pretending that we could put in a ton more rectangles in between. Okay, so our A is t sub 0 and our B is t sub n. So if we are doing a left-hand approximation, right, with any number of rectangles we want, what would that look like, right? Well, each one is going to have a width of delta t, right? So this first rectangle here is going to be the width, delta t, times the height. Now, let's talk about the height of this first rectangle here, right? So for a left-hand approximation, the two values I could plug in to get the height are t sub 0 or t sub 1. Since we're doing a left-hand approximation, we pick the one on the left, t sub 0, and we plug it into the generic function f of t. So the height of the first rectangle is f of t sub 0. Right? And so this, if we had the function, we'd actually plug the numbers in. But again, this is just sort of the generic way to think about this. The second rectangle, again, has a width of delta t. And now the height is f of t sub 1, because for the second rectangle, we're picking the one on the left, which is t sub 1, plus, now I'm going to do plus dot, 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 which means everything in between. And we're going to jump to the last rectangle because, again, we're imagining that we could put in any number of rectangles we want. So what does the last rectangle look like? Well, here we have delta t as the width because the width is the same for all of them. But the height of the last rectangle is f of t sub n minus 1, right? So the rightmost point is t sub n, which means the one before it is t sub n minus 1. So this is the generic way that we write the left-hand sum. We can do the same thing if we want to do a right-hand sum, which is the picture over here. Can't see these as well, so I'm just going to highlight them here, where we know that each rectangle is going to have a width of delta t, only now when we're picking our subscripts, we're going to be picking the rightmost point. So for the first rectangle, the height will be f of t sub 1, because that's the one we're going to plug into our function to get the height of the first rectangle. For the second one, we have f of t sub 2, because we picked the one on the right. And then for the last one, we have f of t sub n. Now, I want you to imagine that we want to fill in 1,000,000 rectangles, right? There's no way that we are going to write out every single term for 1,000,000 rectangles. We know that the more rectangles we put into a small interval, the better our approximation will be, but we're not going to write that all out. So we're going to use summation notation, which you probably saw at some point in algebra or some other maybe geometry, depending on when you took it. And so when we set up summation notation, we want to sum a lot of things that look the same. And so the way summation notation works is we use this sum symbol. We write the things that are the same. So we're summing up things that have a delta t times f of t. Now the thing that is changing is the subscript, right? So the thing that's changing, we index with an I, and then we tell the index where to start, so f of t sub 0, and where to end. So for the left hand, it's n minus 1. This says add up all the terms starting with I equals 0, then 1, then 2, then 3, and stop when you get to n minus 1. So this is how we write what's called the Riemann sum for a left-hand approximation. When we do it with a right-hand approximation, we still have delta t, we have f of t sub I. What's different is where we start and where we end. For a right-hand approximation, our index starts at 1, and it keeps going until we get to n. Okay, so these are the two Riemann sum representations, and the difference again is that for the left-hand approximation, we start at the leftmost index, which is 0, and we don't use the rightmost index, which is n. For the right-hand approximation, we start at 1, so we don't use the 0, and we go all the way until n. And so when we want to think about putting in more and more rectangles, right, to get the exact area under the curve, we're thinking about letting n go to infinity, right? And when we talk about letting n go to infinity, what that means is that when we have an area that we are interested in, right, we're not infinitely expanding this way. We are trying to put infinitely many rectangles in a defined area. So each one, right, is going to be super, super thin. So we're getting less overage and underestimates and making the approximation better. So we want n to eventually get as big as possible. The more rectangles we can fit in, the better our approximation. And what's going to happen is that eventually when n is big enough, our left-hand approximation will be the same as our right-hand approximation, and we will get the exact area under the curve by putting in enough rectangles, okay? So we're going to work on how we do that next class. How do we let n get big? What does that look like? What does that mean? How do we calculate it? For Thursday's class, I recommend if you have a graphing calculator that you own to bring it to class, because we will be doing some calculations on the calculator. And you will need a graphing calculator for that. Okay, so think about all that. Think about how these things intersect, and then we will pick up with this on Thursday in the next section.